Today we will be looking at exponents, and specifically we're going to be looking at exponent laws and how we can simplify expressions by using them. And one thing to know is, like Mr. Lumberg is saying here, if you could use only positive exponents, yeah, that would be great. We write simplified expressions with positive exponents only, and we'll look at that more in just a second. So first off, we've talked about what a power is. This whole thing here, this big 3, little 4, that whole thing is a power. The little number up high is an exponent, the bottom number is the base. The base is the number that we are multiplying by itself, however many times the exponent says. So we've done an investigation, we've looked at what these properties might be, but let's revisit this looking at a couple of examples. So let's say we have a squared times a to the third. In expanded form, that would be a times a, that's a squared, times a times a times a. That's a cubed. So we have a squared times a cubed, and that's repeated multiplication. That we can use an exponent to rewrite. That's going to be a to the fifth. So where does the 5 come from in relation to the 2 and the 3? Well, we're adding. So a to the m times a to the n is a to the m plus n. It's saying if we're multiplying two powers that have the same base, we add the exponents. This property does not work if the base of these powers are different. If they are different, it wouldn't be repeated multiplication anymore, would it? Power of a power. Okay, let's say we have a squared cubed. Well, that's a squared times a squared times a squared. And in all the way expanded form, that's a times a times a times a times a times a. And that rewritten in exponential form as a single power is a to the sixth. So this final exponent, where is that coming from with the 2 and the 3? Well, we can do 2 times 3 to get 6, and that happens to always be true. If we have a power raised to a new exponent, we can take that original base and multiply the 2 exponents together. Finally, the quotient of powers. This one we have, let's say we have a cubed over a squared. That'd be a times a times a over a times a. And remember, when we take something and divide by itself, we get 1. So a divided by a is 1. A divided by a there is 1. And we're left with a to the first power. And again, I asked the question, that 1 at the end, where is that coming from with these original 2 exponents? It's coming from subtraction. So this is equal to a to the m minus n. For all of these properties, the base of the 2 powers has to be the same. Now, power of a product. So here we have 2 things multiplied together inside the parentheses, both being raised to this exponent. And what this property says is we take each of them and individually raise them to that exponent. Similarly with power of a quotient, when we're raising a quotient, a fraction, to an exponent, we could instead take the numerator to that exponent and the denominator to that exponent separately. Now, here's a couple big ones. 0 exponent and negative exponents. So a to the 0, anything to the 0 power, is equal to 1. And where does this come from? Well, this comes from having, let's say we have a cubed over a cubed. That's the quotient of 2 powers. The bases are the same, so we could write a to the 3 minus 3, a to the 0. But remember, anything divided by itself is 1. So a to the 0 is equal to 1. Now, the negative exponent rule also comes from division. Let's say we had a cubed over a to the 4th power. So we have a higher exponent in the denominator. If we use our subtraction property, That's a to the 3 minus 4, which would be a to the negative 1. But if we think of this as repeated multiplication, we could instead do a times a times a over a times a times a times a. And we get a bunch of 1s in here. 1, 1, 1. What's the only thing left over? Well, the only thing left over is this a to the first power on the bottom. And in the numerator, we just have 1. So generalizing what we see here, a to the negative n is 1 over a to the positive n. I like to say that negative exponents move things. And we could extend this a little bit to also say that a to the n is 1 over a to the negative n. And down here on the bottom, I do have a couple of examples. 5 to the negative third is equal to 1 over 5 cubed. Well, 5 cubed we can actually do something with. 5 cubed is 125. So a better way to write that is 1 over 125. The negative moves the power from wherever it is, numerator or denominator, to the other one, and that uses up the negative exponent. It's not a negative exponent.